Okay guys, we're going to do a problem here with the dog barking in the background. Okay. Let's say that the probability of red cars, change my tip smaller here, and I'll erase, I don't like that. So let's go back to tip. This size is good in black. Okay, we're good now. So let's say we have a situation where they tell you that red cars in the United States are 30% of all cars out there. But I do a survey at Park Meadows, and out of 210 cars, I count 73 red ones. So 73 divided by 210 means I'm only coming up with 34%, or 34.8. So I think this 30% number is not accurate. I propose that it's greater than 30%. So this one here would be H null, and this one here would be HA. So I want to see if there's a convincing evidence that it's going to be greater than 30. Now, my conditions and assumptions. First of all, the cars I selected were random, just cars that drove by. The 210 cars would be less than 10% of all cars. I do have 10 successes and 10 failures because, the way around, this way, sorry guys, this way, because I do have 73 cars that were successful being red, and 210 minus 73, whatever that is, 210 minus 73. 137 cars that aren't red. So my conditions and assumptions are met. Okay, go to the next page then. The next thing I do is I have to find my standard deviation, which is the square root of PQ divided by N, not P hat, Q hat, PQ. So this would be 0.3 times 0.7 divided by 210. 0.3 times 0.7 divided by, 0.3 divided by 0.7 divided by 210, and then take the square root of that, would give you 0.032. So we can assume they're normally distributed because we have 10 successes and 10 failures. So graphically it's going to look like this. 30% of the cars should be red, but I'm getting from the previous part here 34.8%. Is that significant? What's the probability that 0.348 or greater would occur? So behind the z-score, we take 0.348 minus 0.3 divide by the standard deviation of 0.032, and that gives us the following: 0.348 minus 0.30 divided by 0.032 gives us a z-score of 1.5 on the nose. So what's the probability of z being greater than 1.5? You go to your normal CDF function, make your lower at 1.5, make your upper infinity, 0 and 1 for your standard deviation and your average, and that turns out to be 0.067. So, if we're using an alpha level of 5, this here is 6.7%. So, since it's above 5%, okay, of an alpha level of 5%, we would fail to reject, FTR, fail to reject the null, and say there is not convincing evidence that the number of red cars is greater than 30%. Okay, so go to the next page here. Not enough evidence this stylus is crappy. To support a number greater than 30%. So, going back to this part, what this number here means right here, 0.067, that is your p-value. That is the probability of having 34.8% cars be red or greater, the chance of that event actually happening. And it did happen, but there's only a 6.7% chance of it occurring. Although that's not considered significant unless it's less than 5% if we're using an alpha level of 5%. Now, if we go to an alpha level of 10%, if alpha were 10%, we would then reject the null and say there is strong evidence indicating that the number of red cars is greater than 30%. Okay? So we reject next null and then say evidence shows there are more than 30% red cars. Okay? All right. That should be a pretty good idea then of how to do a hypothesis test. Now, let's go to what a type 1, type 2 error would be. If we have a type 1 error on the original, remember on the original we got the p-value of 0.067 and we failed to reject. What a type 1 error would be is that we did reject when we shouldn't have. So what that would mean is we think there are more than 30% red cars when there isn't. Because remember, to make a type 1 error you have to reject, which means you take on the alternative hypothesis of there being more than 30% red cars. So we would think there is a higher percentage of red cars when actually there isn't. A type 2 error would mean that we failed to reject the null when we should have. So in context, what that means is we think that the number of red cars is 30%, when in reality the number of red cars is greater than 30%, and from my survey around 34.8%. So therefore, we're misled. We think that the null is true, but it isn't. We should have rejected it. It would have been the right thing to do, but we failed to reject, and that was an error. Therefore, we should have rejected it. So that would be a type 2 error. Okay. Lastly, I want to talk about power. Power is 1 minus beta, and beta is the probability of taking a type 2 error. So 1 minus type 2 error. So if we decrease type 2, we increase the power. Because it's closer to 1, it's a larger number. If we decrease type 2, we would increase type 1. Type 1 and type 2 errors are inverses of each other. So when one goes up, the other goes down. So if we can increase type 1 error, we get more power. Now, in order to make a type 1 error, you have to reject. It's easier to reject if alpha is bigger. So if we can make alpha bigger, it's easier to reject, and that will result in more power. Like 10 hour, I need more power. Lastly, the way to get more power is to have a larger sample size. A bigger N means you're more accurate in your interpretation, so a bigger N will lend to give you more power, making the right decisions. So really what power is in layman's term is that you actually reject when you should have rejected. You do the right thing. If the null is false, and you have the data indicate it's false, then you actually should reject. So it's rejecting when it's proper to reject is a very powerful test, not making an error. So once again, to increase the power, lower type 2, or increase type 1, or make your alpha bigger, because a larger alpha makes it easier to reject. If it's easier to reject, then we can make it easier type 1 or increase type 1, which makes it more powerful. I know it sounds backwards. Having any type of error is bad, but type 2 error is usually considered worse, because the more type 2 error you have, the less power that you have, and you want your test to be powerful. Okay, hope that helps.